Okay, welcome everyone to this week's ZUCCMAP talk. Thank you all for coming. This week we have a very special guest, which is Lukas Münzel, who actually started out with me as a CSC student, but did the unthinkable and switched to mathematics. He's now in his second year. Today he's going to be talking about machine learning, both on the technical ends and also about how it's changing our world and its impact on humanity. So please welcome Lukas.
Great, thank you very much. So welcome to my talk on progress, machine learning, and why to be optimistic about the future. So first of all, why am I optimistic about the future? Well, humanity has seen enormous, unprecedented progress throughout the last 2 millennia and the last 3 centuries in particular. And that has also translated into more education, into less poverty. I mean, this is enormous, right? From 80% to 10%, less than 10% within less than 2 centuries. And it also translates into a very, very direct reduction of human suffering. Okay, and I also want to convince you that you can contribute to this, right? Be it indirectly with mathematics, but also if you want directly. You can do computational biology and contribute to, say, delaying Alzheimer development, and that's going to massively improve the lives of 100 million people. If you solve fusion, well, you solve the huge part of climate change, but also like with the, for example, asthma development and premature deaths because of things like that, you're going to save a few million lives with that, which is amazing. But now let me talk about something more specific, which I'm excited about, and I truly believe that has the potential to result in similar enormous positive change. Okay, so to talk about machine intelligence, let me first start by talking about airplanes. Why that? Because I believe that actually airplanes and the quest for machine intelligence have a couple of rather interesting similarities. Namely, you have some you have some technological measure which increases over time, with which the development of the technology gets way easier. So in the case of airplanes, that's the power-to-weight ratio of our most powerful engines. And as you get more and more powerful engines, it gets easier and easier to develop a fairly good airplane. And right, if you're down here, and right, this on the y-axis is on a log scale, the power-to-weight ratio of engines. And the green line is the power-to-weight ratio of bird muscles. And right, if you're down here, it's really, really hard to develop a proper airplane, like perhaps even actually impossible. But hey, about around the time, we started developing engines which matched the bird power-to-weight ratio. We also developed airplanes. And actually at the time this was also like highly non-obvious. There are articles from the New York Times 9 weeks before the Wright brothers launched their airplanes, which claimed that it would take humanity another 1 million years or so, which is a ridiculously long time span, to develop working airplanes. Okay, and the interesting part now is that we have a very similar type of technological progression for the chips which we use to train these artificial intelligence machine learning models. So this is Moore's law. On the y-axis, you have the transistor counts of current graphics cards, and on the x-axis, you have time. And you see this progresses exponentially. Well, actually, you don't, because all of this is squashed to basically 0, so let's put it on a log y-axis. This trend has been consistent for 50, 60 years. Do I actually know whether it will continue? Not really. I researched this for a couple of hours, and people are divided on that. Like some people from the semiconductor industry claim with confidence, like, no, we're fairly sure this is going to continue. If you ask the CEO of NVIDIA, he thinks it's been dead for a while and is staying dead. If you ask the CEO of Intel, he thinks it's alive and well. Well, okay, I won't try to claim more, other than that predicting the future is quite hard. But even here at the levels we reach currently, we might already start to see interesting behavior. And even if we do not, right, if this trend continues, and like my predictions on the next slide are going to be wrong by 6 orders of magnitude, well, Moore's law means roughly a doubling of transistor counts every 2 years. So if you want 6 orders of magnitude, that's just 40 years. We would see that in a lifetime. Okay. Well, that's depressing. Please don't give up on me. Okay, yes. And also, we're actually not only seeing an exponential increase just in transistor count, so in the computational capacity of the devices we use, but also just in the amount of investments in current state-of-the-art models. So here you see for GPT-4 released in 2019, we were at roughly $40,000. For GPT-3 released in 2020, we were in the order of millions. And for GPT-4, we were at around $100 million, very roughly. Okay. And now, just to give you some more concrete numbers regarding the biological systems, and these comparisons are very, very unfair, right? Because a neuron might be doing quite a lot of computation. Potentially, perhaps we can simplify it to something which we can implement with like some tens of thousands of transistors. We don't really necessarily know. But I thought it was interesting to make the comparison explicitly, and also just because I was actually surprised at how much computational capacity the brain potentially has. So the brain is at 10 to the 11 neurons. Actually, we're quite matching that quite closely with transistor counts now, and it has roughly 10 to the 3, so 1,000 connections for every neuron. So every neuron is connected to around 1,000 other neurons. And those fire at a rate of roughly 1 hertz to like 100 hertz. So actually we're sort of comparable. And again, if we actually need 6 orders of magnitude more transistors to match the computational capacity of the brain, well, we'll wait another 40 years or invest 6 orders of magnitude more money. Okay. But now, more concretely, let's try to derive show how current machine learning models work. So we start with an incredibly simplified model of an artificial neuron. How does that work? Well, we have some blob. We call that blob neuron. It takes some input from other neurons, and those inputs are all scalars. And we try to output another scalar somehow. Well, what's sort of the simplest aggregation function which we could use? Well, let's just pick something which is linear if we interpret this thing to be a vector. And then let's just add a constant. So we call these things here, which, weigh the output of these inputs, weights, and the b term would be commonly called bias. Okay, good. And now the basic concept of machine learning is just, and you will see this again and again and again in this talk, how about we just scale this up? Okay, so we use more and more neurons. They all combine the information in the fashion I just described. These weights, so all neurons in the first vertical stack are connected to all neurons in the second vertical stack, and so on. And all these weights between those neurons are different. And we call those vertical stacks layers, and this dimension we call depth. Okay, good. Let's try this. Maybe it works, maybe it doesn't. Okay, and for the time being, let's just assume that the weights are given by some very nice and intelligent computer science major. I will explain afterwards how to actually get them. Okay, so here for this data set, we see that the model is actually capable of separating between the points. So what do we do here? Oops. Can I? Okay. Right, we just take 2 input points, which represent the x and the y coordinates of the points we give the model. And then if y1 is higher than y2, we predict that the point is blue. If y2 is higher than y1, we predict that it is orange. And now, as you can see, this works quite nicely. However, let's try it on a different data set. This is horrible. Any ideas what might be going wrong? Oh, yes?
I think we're trying to figure out the linear separation, and this cannot happen here.
Exactly. And we can only figure out linear separations because we are taking affine combinations of affine combinations. So if we take something my God. If we take something of this form here and we multiply it by a scalar, or we add two things of this form, then, well, we just get another thing of this form. So taking linear combinations doesn't really increase our expressivity at all. So what could we do instead? Well, a dead simple fix would just be to, well, add some nonlinearity. Do exactly what I just described, and plug it into some function which is nonlinear. In this example, it's what is also quite commonly used in practice, ReLU standing for rectified linear unit, right? It's, well, linear for values bigger equal to 0, and otherwise for values smaller than 0, it's just 0. Great. Okay, let's be a bit more specific with some details. First of all, I want to index the weights a bit to afterwards be able to make more specific claims. So let's say that W subscript I superscript J is the weight that connects the ith neuron of the second to last layer with the jth neuron in the last layer. So for example, W12 would be the neuron connecting the weight connecting the second neuron in the second to last layer with the first neuron in the last layer, and WN2 would be the neuron connecting the weight connecting the nth neuron in the second to last layer to the second neuron in the last layer. Okay. Now, what would we like these yi's which we extract to have as features? Well, first of all, if they're going to be probabilities, which is what we want to extract in the end, because then for every point we can predict the probability that it is blue or orange. Well, if they're probabilities, they should sum to 1 and they should be non-negative. So what do? We plug those values into some non-negative monotonically increasing function and then just normalize. So we take the sum here e to the ai. The exponential function is non-negative, monotonically increasing, and then we just divide by the sum of e to the ai over from j equals 1 to n. So if we then sum all those yi's up from I equals 1 to n, well, the denominator doesn't change, and then the numerator in the end, you can plug the sum into here. You get that the denominator equals the denominator, the numerator equals the denominator, and you get 1, which is exactly what we wanted to have. Okay, neat. Then what we also need to do is we need to rigorously define what we actually mean by the network performing badly, the network performing well. So what we do is we introduce the so-called loss. What does the loss do? It measures how badly our model is performing, in the sense that if the loss is higher, our model is performing worse. So what we're then trying to do afterwards is try to minimize the loss. Good. So the loss we then define as the negative. Okay, if we are given m samples, we define the loss as as minus the expected value, or well, the average of the predictions our model makes for the correct classes. Meaning that, for example, let's say we're only given one picture for simplicity, so before we take the average, let's say that is a picture of a cat. And like our neural network is supposed to differentiate between pictures of cats and pictures of dogs. And we have a picture of a cat, and we know it's a picture of a cat. So we feed it through a neural network, and the neural network confidently predicts, well, I think there's going to be a like 30% probability that the picture you just gave me is a picture of a cat. And then we just take the negative logarithm of those 30%, and that is then our loss. And right, in reality, we just do that with n different samples and then take the average over them. And well, this might be sort of hard to and confusing to wrap your head around, so let's just think about this in some more detail. So the logarithm is monotonically increasing, and you see that if we take the negative logarithm then, it gets higher and higher the closer to 0 we get, and if we actually got 1, which is what we would ideally want to have, right? If we have a picture of a cat, ideally the network should give us 100% probability that the given picture is a picture of a cat. So if we take the negative probability, we get higher and higher values of the negative log. We get higher and higher values of the loss as we go to 0 with a probability estimate of the correct class. Okay. Now, with all that in mind, how do we change the weights? Well, let's perhaps first give some intuition for what we're going to do. Our ReLU function is differentiable everywhere except 0. Linear functions, and if we add a constant certainly as well, are still differentiable. And our entire network is just a composition of such functions, so they're still differentiable. And hence, we can just derivate with respect to each weight. So very intuitively speaking, perhaps, you'd fix some weight and you look, okay, if I wiggle this weight around a bit, how does my loss change? And then you just take a tiny step towards the direction in which your loss decreases. And you first do the figuring out how much wiggling around the neuron changes the loss step for all neurons simultaneously, and then you change all of them by a small step simultaneously. And then you just repeat that process. So how might that look for like a simple function? Well, okay, here the derivative is positive, so we take a step into the negative direction of the derivative, and if you will, in dimension, that's a step towards the negative direction of the gradient, right? Because your function is actually, your neural network is actually a function of all the weights which define it, and that is also like the only degree of freedom you have, modulo perhaps the biases. Okay, so we take a step towards the negative, towards the direction which minimizes the loss. We again, like here, the derivative would again be positive, right? The function increases as we increase x. So we again take a step, take a direction towards the step towards the negative x direction, and we repeat that. And now we would need a smaller step size to actually converge to a minimum. Okay, good. Let's see that in practice. Okay, so here we use exactly what I told you about earlier, the ReLU activation. And slowly but surely, it converges to the, well, a quite acceptable solution, I would say, and yeah, near optimal. Nice. And we can also try it on a slightly different data set. Oh, well, this is interesting. We could also, for example, increase the learning rate, that's the step size, and then it would converge a bit faster. But again, as I showed you, if you then choose a too large step size, you're going to step around the minimum and not actually converge, which is also why in practice we actually decrease the step size throughout training. Good. Also, if anything is unclear or you have questions, do feel free to ask them. Oh God, I'm good in time. Nice. I'm really, what? Okay, I'm much faster than when I practiced, much faster. Okay, okay. Now we have sort of classical neural networks defined reasonably well. But, well, language models actually process text, and it's not super obvious how you now handle a sequence of text and feed it into the structure we defined so far. So we actually define something on top of these classical neural networks, which we just defined. Also, one thing, a complete detail, but we call those classical neural networks which are just defined multi-layer perceptrons, right? Multiple layers, and perceptron, you can basically, for the time being, just assume that it's synonymous to neuron. Okay, and short form for multi-layer perceptron, MLP. I will use that afterwards. Good. Okay, so we're given some string of text. What we do is we cut that text into reasonable chunks. So for current language models, that's maybe like 40,000 different chunks of text which we can differentiate. Okay, and for short or very common words, those chunks correspond exactly to words, but as you can see here for, I'm not going to pronounce that on stage, you have, you split the word into these different things which sort of vaguely remind you of syllables perhaps, but again, if they're more common, then you might have longer and longer ones. I hope that sort of makes sense. Okay. And, well, and right, if you have the same, and we call those chunks tokens. If you have the same token twice, so if you have the same text chunk, then you translate that to the same integer, right? So here, for example, right, we have the sentence, why did the cats chase the dogs? And you see here that the is matched to 279, and the next, I mean specifically actually white space, the is also matched to 279. Okay, neat. Well, these are discrete values. We sort of want something in RD because that is also what, for example, we could then process with our MLPs. So what we do is we just learn some embedding into, let's say, RC of every one of those tokens. And, well, how do we define this embedding? Well, we just initialize it randomly, and then we learn how to improve it with exactly what I just mentioned, stochastic gradient descent for every element in the matrix defining that embedding. Well, figure out if you wiggle it around a bit, how that improves the loss, and then take a tiny step towards the direction which improves your performance. Okay. Good. And now comes the actual attention part of transformers. Also, perhaps I should mention this in general. Transformers are the technology behind all these large language models, ChatGPT, etc. you've seen. Okay, and attention is the mechanism on a sort of more micro level. Okay. We have three matrices and our vectors. Our vectors live in RC. Let's say we have T vectors. These vectors are the embeddings of the tokens of text we were just given. And the matrices are in M cross C matrices, so they could take those vectors and transform them to something living in RM. Okay, and now we just do exactly that. We calculate Ki as, oops. Okay, this should definitely be a K, I'm sorry. This big V here should be a K. I apologize. Okay, and we do the exact same thing with Q. So, okay, quickly, what do the letters stand for? Q queries, K keys, and V values. And we will see just in a second why those names actually correspond to meaningful things which we then actually do with those. Okay, now we define W hat ij as 1 over the square root of M times Qi dot product Kj. Okay, how can we make sense of that? Essentially, every token generates a query by just applying a linear transformation to its embedding. And similarly, every token defines a key corresponding to that token, again, with a linear transformation. And you can imagine, for example, let's say you're a verb and you want to know what the gender of the subject that is matched to you is, then you could, with this, write a query that asks for the gender corresponding to your subject, and then the noun which has that subject could inform you about that by setting its ki to be collinear to that qi. Okay. And right, because we then take the inner product, that wij is high, and that wij then corresponds to how much we care about the input of the jth token when generating our new embedding for the ith token. Okay. And then, well, we just normalize again. The exact same way we just did it 5 minutes ago for probabilities. So that they sum up to 1 and they're all non-negative. Yes?
Right now you talked about the gender, etc., but verbs also have to know in some languages the number
Okay. Very fair. We will get to how to handle separate requests in like 5 minutes, but it's a great question. Keep it in mind because actually it's good motivation for why we need to add something later. Yes?
Basically, we're considering all possible pairs or combinations of words in the same sentence, and we can just imagine them basically all in the table, and we complete this double hat so as to correspond a certain way to each possible combination of these pairs, and then thus we can in the next round filter out the most relevant ones and get out the corresponding connections.
2 details. First of all, we actually only update. Let's say we're given some sentence with 3 words. Then for the second word, we actually only consider the queries of the keys of the second and the first word. So it's actually not the entire square matrix, but if you will, only the upper diagonal. Yes. And I think things will also make more sense in like 40 seconds. Okay. So we take those normalized weights, and then we just generate our new contextualized embedding for our token by applying the matrix on the xj and scaling it by how much the query of the ith token matched with a key of the jth token. Okay. Should I repeat that, or does that make sense? Okay, good. Great. Okay, so now, long story short, I basically defined a way, given T tokens, to transform them into contextualized versions of those T tokens, now living in our M, right? Because V is this M by C matrix, so now we have tokens in our M, not in C anymore. Okay. What do we do now? Well, let's just abstract away for a second and consider this as just one system, right? It takes T tokens, it outputs T contextualized token embeddings. Okay. Well, we just defined this beautiful multi-layer perceptron. Why not actually use it now? And specifically, how do we use it? We take vectors in, you can imagine them to, they take, let's say, M numbers, but every one of our token embeddings, our contextualized token embeddings actually has M numbers in it, so we use the same multi-layer perceptron, the same feed-forward neural network to process all of them. And this then just gives us yet another representation for the exact same token embeddings. Okay. Now we come to your question. Well, right, I would potentially also like to know a bit more, right? It also might want to know about its object, as you said, perhaps like about how many of the subject it relates to are present. We want a bit more information. We want to be able to handle that information in parallel. So what we do is we just make copies of all our vectors and we feed them to multiple copies of the architecture I just explained. However, we use separate key, query, and value matrices for all of them and separate multi-layer perceptrons for all of them, right? Because otherwise they would not actually be computing different things. Okay. Now remember that we could choose our M freely, right? The dimension into which we embed. We had those. We had the value matrix, and the value matrix is C by M, so no, M by C, and we can choose M freely. So what we just do is let's say we have the C, which actually corresponds to channel dimension. I maybe should have mentioned that. We have, let's say, C equals 100, and then we set for every attention head. Let's say we have 5 of them. We set M equals 20. And the advantage of that is then we have a very simple way of getting 100-dimensional token embeddings again. Well, we just concatenate them. Right? You take let's say for the first token embedding, you take the output of the first attention head for that token, you take the output of the second attention head for the token, you just put them together, stitch them together, and you get a new vector. And that, does it make sense? Okay, good. Great. And then we feed them into our MLP. Okay. Subtleties which I don't want to go in depth about, but I also don't want to lie to you. We actually normalize. Before we feed them into the MLP and before we feed our contextualized token embeddings or original token embeddings into the attention heads. Honestly, this normalization helps significantly with performance. I don't think it's conceptually super duper interesting. It's called layer normalization if you want to look it up. Okay, yet another slight complication. We're doing a lot of relatively complicated processing here, and at initialization, these matrices are all random, they're doing weird stuff, they're transforming our tokens in super weird ways. And for example, if we just would like to maintain the information which we already had, we would have to work quite hard to do even just that. So what we do is we actually per default just take our our stream of inputs and we just maintain that. So the entire architecture which I just described sort of works on the sidelines, and then right here we get our vectors in RC. We, as I described above, after concatenation, we again get a contextualized embeddings in RC, and then we can just add them normal vector addition to each of those vectors to again get vectors in RC. And we just do the exact same thing for the multi-layer perceptron. If this is confusing, I also don't think that this step is super conceptually relevant. I just wanted to actually describe the architecture more or less properly. Great. So, yes? Okay, yes, I see, good. Okay, now we call this entire thing now an attention head. And, well, what is sort of the natural thing if we have something which maps our token embeddings in RC to contextualized token embeddings in RC? Well, the input dimension is the same as the output dimension. Let's just stack them together, stack them together, stack them together, stack them together. Okay, and we again get outputs in RC, right? Because that is invariant under our attention blocks. And then to actually get an output, well, we normalize, we feed it into some matrix, and now in the beginning I told you that we use roughly 40,000 different tokens between which we differentiate. So if we now take those vectors in RC and we multiply them with this matrix W, for every single token we get a vector that is 40,000 dimensional. Okay, now what could we do with that vector? Well, we normalize it in the same way I described with the right exponentials and then normalizing. So we can basically, after normalization, we can assume that all the entries in that vector are non-negative and sum to 1. So it's sort of natural to assume that actually they describe the probabilities of tokens. And specifically, every token describes then the probability of the next token. Let's perhaps see this a bit more concretely. So, right, we have the sentence, the boy went to the, and then you would apply W to the contextualized token embedding of the, and then you apply our nice normalization to make sure that the entries in that 40,000 dimensional vectors are all non-negative and sum to 1. And, well, then you get a probability distribution over the tokens which could appear next. And then you can sample from this. You have to be a bit careful about sampling. You get bad results if you just always sample the most probable one. But, right, now we sample a bit cleverly from that. And then we can just take that thing we sampled, append it to the end of the sentence, and run our model again and get a new token, run a model again, get a new token, run a model again, get a new token, and like that generate, if you will, small novels. Okay. I mean, or if you have the resources, also more than small novels. Okay. Are there any questions so far? Yes? Good question. I mean, basically the normalization sort of heavily helps with that, but I had projects where just, it explodes completely. You don't really know why, you don't fix it, and we just worked on another thing. Like, it's a bit hand-wavy. We don't, I mean, perhaps people have tried to prove it for, probably people have tried to prove it for simplified versions, and for example, with the layer norm, we know that that helps with numerical stability, but I feel like this is like, it's in part also an empirical science, let's say it like that. But, and also, right, you can, a very important point actually in that regard is to initialize your matrices cleverly. Because if your initializations are too small or way too large, everything's going to suck and gradient descent is not going to do a whole lot for quite a lot of time or actually never. So, yes. Yes?
In terms of more practical stuff, so how big of a performance impact does the number of words make? So how long do you keep doing this? You mentioned expo novel. Is that like how much harder does every next word get than all?
I mean, okay, I see. Okay, if you compute full attention on the entire thing, then sort of fundamentally it's quadratic in the amount of tokens you feed into your network, right? Because we compare, well, all combinations divided by 2, because we only consider like the tokens which are before our token. However, you can then, which is also done in practice, you can only consider tokens which are like less than, let's say, 100 words away from you, right? And then it's again linear, but on the other hand, you don't actually get that much context. If you do it naively quadratic, let's leave it at that. Okay. I have some more interesting slides, and I'm very happy that I actually get to them. Okay. We have these data points. Does someone have a good idea of what function to feed to these data points? Yes? Yes, great. Amazing. However, I have an alternative hypothesis which fits the data points way better. Okay, can someone articulate what is, because like intuitively it's sort of obviously wrong, but can someone articulate what is wrong with this hypothesis? Yes? Okay, great, sure, yes. There's also another quite nice way to think about it. Basically, there's a trade-off between how well your model predicts the test points you're given and how probable your model is. And if you trade off smartly between those, that also helps with performance. So, what do we do in practice? For example, if we're given our neural network, whatever, well, when we give it our batch of examples, we just randomly deselect some of the neurons we have in here. And how you can imagine the effect of that working out is that features need to get less disentangled in a sense. Let's say you're given some pictures of a cat. And, well, if you're very smart, you can like start to remember, okay, if I have a picture that was like taken in Westminster at 12 a.m. on a Monday, then it's a picture of a cat. But if you remove any of those qualities, if it's not taken at 12 a.m., then there might be another picture taken on a Monday in Westminster. So if you On the other hand, if you remove some of those things, your predictions get worse. So if you want your predictions to be stable under removal of random nodes, a good thing to do is to make them more independent and also more relevant, right? Because, for example, if you have something that is like furry, small, petable, and with like pointy ears, well, if you remove any of those qualities, it's still a cat, or probably still a cat. Okay, and we actually have time for this. I'm very happy. So I trained a small language model on Tolkien's Lord of the Rings. This model has seen absolutely nothing except Lord of the Rings. And let's just quickly see here how well it performs. And we have... Thank you. How much time do we have? 5 minutes, great. Okay. And please load. This is a bit slow. Okay, I'll talk about what to expect. Right, if we overfit to the data we were given, so we matched the training data too closely, then actually we will get better results on the training data, which is exactly what we see. So here, the blue line is mini GPT no dropout with layer norm, so with the normalization. And you see, hey, amazing, it actually performs better on the training data set. And let's just use the red line as comparison. The others are doing some interesting things, which I might get to later. But actually, if you then look at a separate data set, which you didn't show the model, so other parts of Lord of the Rings, which the model hasn't yet seen, it actually gets drastically worse. Yes?
So what are you comparing what it generates to the original text, or what do you mean it performs better?
Okay, yes. We look at the predictions of the model as to what the next token would be, and we just say, okay, is that right or wrong? With exactly, and specifically how we compute that is exactly with the loss I defined. It's actually really the exact loss I defined. And also the same activation function in the last layer.
That's a good question. So how do you decide whether it's right or wrong? What would be the right answer?
Okay, the right answer is the one that was actually in Tolkien's Lord of the Rings. You just give them some text and that text determines the truth. But you raise a quite valid question, right? Because on the other hand, this also means that if you feed horrible training data in, then your model's probably not going to be particularly good. And actually, which is also quite nice to see, because I was a bit annoyed that I just had to drop that normalization in randomly, and I couldn't really find a nice intuitive explanation of why it's actually needed. Here we just see empirically that it's needed. So the other two lines here, in purple and green, are without layer norm, and the other two are with layer norm. And we see that it performs drastically worse, which is sort of nice to see empirically, I think. Okay, good. We have another 2 minutes for one detail, which I would love to get to as well. Okay, the way I explain it right now, something important is actually missing. Namely, how do you think the model is going to answer these two questions? Or do you think it can differentiate between those two questions? Yes?
Not really, because we haven't included in positional coding.
Yes, exactly. Okay, you also used the correct technical term. Our model doesn't really have any idea of where words are. This combination in this attention mechanism I described doesn't include information of relative position. You only know that the words which gave you context are the words which appeared before you. But the token football couldn't directly infer that Mary was the subject and Robert the object. Except if maybe Robert then figures it out via... you could perhaps figure it out with word over order, because every word knows which words are ahead of them. But a way easier thing to do would be to just explicitly give the token embeddings information about where they're located. So we do that. There are multiple ways to do it. For example, you can add sine waves of different frequencies, and then based on the values of sine waves of different frequencies, you can figure out where exactly your token is, and you also have like a nice measure of similarity. Well, okay. Thank you very much for your attention. That's the presentation.